Power augmentation devices. As an aeroplane climbs, density decreases, therefore the power output of a normally aspirated piston engine reduces. This loss may be alleviated by pressurizing the fuel charge going into the engine. One method of doing this is using a supercharger. A supercharger is an engine-driven air pump which increases manifold pressure and forces the fuel-air mixture into the cylinders. The higher the manifold pressure, the more dense the fuel-air mixture and the more power the engine will produce. Note, typical superchargers boost manifold pressure above 30 inches and volumetric efficiency can be in excess of 100%. In other words, better than at sea level. A supercharger is positioned between the fuel metering device and the intake manifold. They are usually driven by the engine crankshaft through a gear at one speed, two speeds or variable speeds. They can also have a number of stages. A stage represents an increase in pressure. The supercharger consists of an impeller which accelerates the fuel-air mixture outwards and a diffuser in which the kinetic energy of the air is traded for pressure energy, which is similar to a centrifugal compressor. An early version of the supercharger is the ground boosted type. Engine power is increased to all altitudes, however the engine power will still decrease with altitude in the same way that it does in a normally aspirated engine. Note that manifold pressure is measured after the supercharger. And also note, a diffuser is that part of a centrifugal compressor that transforms the high speed, low pressure gas into higher pressure. Here's a graph of brake horsepower with altitude. And although there's a decline in the ground boosted engine compared to the normally aspirated engine, and they seem to parallel each other, what can be noted at sea level and at all altitudes, the ground boosted engine has a higher brake horsepower. On some engines, sea level power can be maintained to a specified altitude, and these engines are said to be altitude boosted. With this type, there may be a power deficit at sea level due to the power taken to drive the impeller. However, as the aircraft climbs, power increases as a result of decreased temperature of the air and decreasing exhaust back pressure. At sea level, the throttle valve of a supercharged engine must be partially closed in order to prevent excessive pressures developing. As the aircraft climbs, the throttle valve must be progressively opened in order to maintain the same manifold pressure. Eventually a height will be reached where the throttle valve is fully open. This is called full throttle height, and if the aircraft climbs any higher, power will decrease. Note that the supercharger effect depends on the speed of the rotation of the impeller. Therefore, each power setting will have a different full throttle height depending on engine speed and manifold pressure. The full throttle height at a rated power setting is known as the rated altitude. Rated power is the maximum power at which continuous operation is permitted. An automatic boost control is used to automatically control boost pressure through the movement of the throttle butterfly valve. For example, as the aircraft climbs, the boost control will be gradually opening the throttle valve to maintain the selected manifold pressure. When the throttle valve is fully open, the manifold pressure will decrease with increasing altitude. Some superchargers use two speeds in order to achieve better performance. The speed change is achieved by using two different gear ratios, and the speed change is made by activation of a cockpit switch. Takeoff will be made at the low speed setting, and at a specified altitude the high speed setting will be selected. The drawback with the supercharger is that it uses a large amount of the engine's power output for the amount of power it actually produces. This problem may be avoided by using a turbo supercharger, otherwise known as a turbocharger. Turbochargers. The turbocharger is powered by the engine's exhaust, i.e. it recovers energy that would otherwise be lost from the hot gases. The turbocharger can be controlled to maintain rated sea level horsepower up to the engine's critical altitude. Critical altitude is the maximum altitude under standard atmospheric conditions at which a turbocharged engine can produce its rated horsepower, i.e. when the turbocharger reaches critical altitude, power output begins to decrease. If you look at a similar graph that we looked at with superchargers, the brake horsepower for the normally aspirated engine declines with altitude, but for the turbo supercharged engine it remains constant until it reaches a certain density altitude and then declines. The turbocharger is located between the air intake and the fuel metering device. It consists of a centrifugal compressor and a turbine mounted on a common shaft. Exhaust gases spin the turbine and the impeller draws air in and compresses it. Turbocharging causes the temperature of the induction air to increase as it is compressed, so to reduce the temperature and lower the risk of detonation, an intercooler is used. The intercooler is a small heat exchanger. It uses ambient air to cool the compressed air before it enters the fuel metering device. If all the exhaust gases pass through the turbine, then it is possible that excessive manifold pressures would result, especially at sea level. This is called overboosting. If the amount of exhaust gases passing through the turbine is limited, then the power produced by the turbocharger will be limited at high altitudes. Therefore, to control the amount of exhaust gases passing through the turbine, a valve called a wastegate is used. It is mounted in parallel with the turbine. When the wastegate is fully open, all the exhaust bypasses the turbine. When the wastegate is fully closed, all the exhaust gases are routed through the turbine. The wastegate position can be adjusted manually or automatically. This diagram shows the location of the wastegate relative to the turbine. Wastegate operation. The valve is held open by spring force and the valve is closed by oil pressure taken from the engine lubricating system. A variety of controllers are used to vary the oil pressure at the wastegate. An absolute pressure controller prevents the compressor outlet pressure from exceeding a specified maximum value. It consists of an aneroid capsule which is sensitive to compressor outlet pressure. If the pressure is too high, oil will be bled away from the wastegate valve, thereby opening the valve more. The variable pressure controller. This functions in a similar way to the absolute pressure controller. However, the difference is that a cam linked to the throttle controls the position of the aneroid capsule. A density controller differential pressure controller is used on more sophisticated systems such as the sea level boosted engine, which maintains sea level performance up to critical altitude. The density controller regulates oil flow only during full throttle operation and below critical altitude. The differential pressure controller operates at all positions of the throttle rather than fully open. A pressure ratio controller. Some engines are restricted to a maximum altitude at which they are allowed to maintain their maximum rated manifold pressure. In such cases, a pressure ratio controller is mounted in parallel with the absolute pressure controller. It monitors ambient pressure and pressure of air before it enters the fuel metering device, with the aim of preventing the turbocharger from boosting to more than 2.2 times the ambient pressure. Rate of change controller. This ensures that pressure of air going to the fuel metering device does not increase too rapidly. A pressure relief valve is located in the induction manifold and it opens if overboosting occurs.